Okay, our last topic in waves is on the reflection and refraction of light. Although I suppose it could be for any type of wave because all types of waves reflect and refract, but we're going to focus on light. We have learned so far that one way that we can show the propagation or the movement of light is to draw in wave fronts and then indicate that they're moving in a certain direction. Okay, we've done that before, so like here's some wave fronts that are moving, and let's say that they're moving to the right. You could draw some wave fronts. Okay, here's some other ones. I wish these were a little more parallel, but what are you going to do? You could even draw wave fronts that are kind of concentric so that they're going out from some center location. That's a lot of drawing though, and it can get a little confusing. I mean, we know that wave fronts just show points that are all in phase with each other, but there's got to be an easier way to draw light. I'm going to show you that easier way with this little simulation that I just found. It's actually pretty useful. So I'm going to click resume, and what we're looking at here, we have our plane wave like we're used to, a wave front, but look how that's traveling. I'm going to pause this for just a second. It's traveling, and I know it doesn't quite look like it from the screen, but it's actually perpendicular to this line with the arrow on it. That line with the arrow on it is called a ray. And that's important because we're going to spend this topic drawing, instead of wave fronts, drawing rays. Now notice that we also have, we've kind of created this this other wavefront here that is perpendicular to this ray. We've created this wavefront here that's perpendicular to this ray. Now I'm going to talk about what those mean in just a second, but to start with, we're just going to talk about rays. Okay, so we're just going to get practice drawing rays. An easier option than drawing a whole bunch of wavefronts is to draw a ray. A ray is a line that is perpendicular to the wavefronts, and it points in the direction of the wave's travel. Points in the direction that the wave is traveling in. So that might look like this. Okay, there's a ray. Instead of drawing all these lined up wavefronts, we can just draw a ray to indicate the direction of travel of all those wavefronts that constitute the wave. Okay, if this wave is repeating over time, we can, instead of drawing a million different wavefronts, we can just draw a ray. Okay, it's got to be perpendicular to the wavefronts. For something like this, we could draw rays going perpendicularly outward, like so. Okay, all of those would be rays. Now, light rays will move in straight lines. Light doesn't kind of curve, it doesn't wiggle. It moves in straight. I suppose you could say, if we're looking at rays, you know, for diffraction, it's more useful to draw wavefronts because we know that they spread out when they go around a boundary. But a light ray itself will move in a straight line in one direction until it comes to a boundary between two different media, two different materials. At that point, part of the ray moves into the new medium and part stays in the first medium. Matter of fact, we saw this before with this picture where we saw here's the incoming ray. Part of the light of the laser beam goes into the prism, part gets reflected back out. That's kind of what we're talking about here. Okay, this is essentially the same sort of picture. The ray that approaches the boundary in the first place is known as the incident ray. That's this ray right here. The ray that remains in the first medium that bounces out is known as the reflected ray. And finally, the ray that passes into the new medium is known as the refracted ray. And this is the ray that we are usually most interested in because refracted means bend. It means to bend, I should say. So you can see the incident ray comes in. The refracted ray is not in the same direction as the incident ray. In most cases, this ray does not continue moving in the same direction that it had in the first medium. Very interesting. You'll notice that since these rays are all moving in different directions, we want to measure their angles. We want to measure something to do with their angles. So each ray's direction is measured as an angle between the ray itself and what is known as the normal line. Now, we've used this word before in physics. Normal, to you guys, should mean perpendicular to. Remember, the normal force is the force that is perpendicular to the surface. It doesn't mean straight up all the time. It means perpendicular to the surface. Thankfully, the surface here, so normal in general means perpendicular to something. In this case, it means perpendicular to a boundary between the media. It's an imaginary line that is perpendicular to the boundary between the medium. Thankfully, in this example, the boundary is horizontal, so the normal line is just a vertical line. Doesn't have to be like that, though. But notice that all of the angles are measured from one of the rays to the normal line, okay? No matter if it's incident, reflected, or refracted, every angle is from the normal line to the incident ray. This angle does not matter. This angle does not matter. This angle does not matter. The ray to the normal. That is what you need. Something that you can see just based on inspection, and you probably did this in like 6th grade science, is that the angle of incidence is related to the angle of reflection. The angle of incidence, as a matter of fact, is equal to, these are equal angles, the angle of reflection. That will always be the case. Okay. Matter of fact, on our waves, on the waves part of the reference tables, we're even given that. Angle of incidence, theta I, equals angle of reflection, which is theta R. Now, I don't like that they used theta R. I prefer to do something a little different. So I write this as theta I equals theta, and I'm going to do REFL. Because we also have a refracted ray. We've got to tell the difference between reflected and refracted. Okay? So theta I will equal theta REFL, theta reflected. So notice that these angles are equal. However, it's very clear that the incident angle is not equal to the refracted angle. The refracted ray bends, and it's a little complicated as to why it bends. It bends due to the fact that the speed of light in different materials, in different media, is different. The speed of light is slower in different media than in a vacuum. Vacuum is the empty space is where light travels the fastest. If there's any sort of material, whether it's air, water, glass, diamond, whatever, light will travel slower. In air, it barely travels slower, like almost no difference. I'm going to show you an application for this, but I'm going to explain it first. If a wavefront approaches a boundary at an angle, then what that means is, since light isn't usually just a ray, it's like many, many rays of light coming in, many different waves all coming in this direction. Part of the wave front will enter the new material. I need to move this up, I'm sorry. Part of the wave front will enter the new material before other parts. So if you're looking at this picture, we have some wave fronts here. The left-hand side of the wave front, okay, the light rays over here enter before the light rays over here. So the light that's over here, automatically, if this material is denser than a vacuum, this material here slows the light ray down. So what that does is it means the light here does not travel as fast. If we're still investigating, if we're still trying to show all the points that are in phase, that means that these points over here are just not going to move as fast as the points that are still in air or whatever, or the other material, okay? That's less dense. And what that does is it kind of reorients all of the wave fronts toward the normal line. Okay, if we're going from less dense to more dense. Makes part of the wavefront slow down before other parts, since the wavefront consists of all points that are in phase with each other. The front seems to bend as it transitions between the media. And I think this is going to be best seen with this little application here. Okay, so we're going to, what are we going to do? Restart. Okay, so we've got a wave front coming in. Now remember Huygens' principle. Huygens' principle says that on a plane wave, all points on a plane wave can be treated as sources of the wave, and they keep propagating. So watch what happens. We're going to resume. Okay, it's going to hit this first point. Really, there should be infinite points, but you can't have infinite points in a computer simulation. And watch what happens. We're going to treat this boundary, okay, all the points along this boundary as sources of the following waves. So it hits that one point, and that point starts to, well, part of the wave is going to be reflected. That's the part of the wave that's coming out circular in yellow. Part of the wave is going to be transmitted, though. That's the wave that's starting to come out in blue. Notice that for the blue part, the wave in blue, this is going to be, let's say that this is more dense. Light moves slower in this part than in this part. So the wave hasn't traveled as far. If I resume, now some more parts are going to be hit. Okay? So what we see, I'm going to keep running a little bit farther. So what we see is the waves just haven't traveled quite as far in the blue material, where the light is slower, than the yellow material. But look at this. Remember how all those wavefronts kind of lined up and we got a plane wave? That's happening here, and that looks pretty much to be the same angle, if I were to draw this straight up, as the angle that this one came in at. This one, however, the wavefronts are not, they're not in the same direction as this wavefront. The wavefront seems to be a little bit off to the side, a little bit slower, and that's because of how slow the light is traveling in this material. Because it's traveling slower, the waves don't have to travel as far to catch up with one another, so they kind of almost reorient themselves to be almost more horizontal in this picture. If we let this go, we see that this plays out some more. I'm going to go to the next step. And this, the only unfortunate part about the simulation just kind of takes forever to load. We can see that those wave fronts that end up happening because of Huygens' principle, because of the treating all the different parts of the wave as the source, they end up being perpendicular to this ray down here. So what we end up with is we had an incident ray, we had a reflected ray, and now we have a refracted ray. And because the position of the wave fronts that all line up, all these points are in phase right here, has kind of been reoriented, that's going to reorient our ray as well. Our ray ends up bending closer to the normal line in this case. And we can actually see that this continues to happen if we have multiple waves coming in. We'll actually get to see multiple wave fronts be reoriented or bent. Okay, you can start to see them forming now in the blue material. You can see the wave fronts as they move in. Notice that they're not moving as fast, and notice that that wavelength is shorter. The waves, and I know it's tough to see because now you got waves all over the screen, but the wavelength in the yellow material is actually greater. The wavelength in the blue material is actually shorter, and that's where it's moving slower, and the wave has bent. I'm going to pause it there because now it just gets confusing. Okay? That is the science of why light bends when it transfers into a different material. Okay? You are used to seeing this. You see this all the time when you see if you put let's say a pen in a beaker of water and look at it from a certain angle. It looks like it's bent. It looks like it's broken. It's really not. It's a trick of the light because the light is literally changing direction as it comes to you and tricking your eye into thinking that it looks like the pen is broken or something impossible is happening. That is the refraction of light. That is what's happening there. Now, we're going to come back to the refraction of light because that's the main mathematical part of this topic. But we're going to take a detour into the speed of light in different materials because that's why refraction happens. Refraction happens because the speed of light in different materials is different, and this is what causes the wave fronts to kind of change their direction, and it's what causes the rays to change their direction at a boundary. We know that light travels at different speeds through each of these different media according to, we've been saying the density of the media, okay? And that's in general kind of true. It's not the full story, once again, but it's in general kind of true. Density. The speed decreases for denser media because the wavelength decreases. And really, I guess it's the other way around. The wavelength decreases because the speed decreases when the light transitions. However, for a single light wave moving between two different materials, two different media, the frequency remains the same. Okay? The way I kind of think about this is the frequency's already been created. Why does the speed depend on the quote-unquote density of the material? I think it's this is my explanation. I don't know how right it is, but a denser material, there's more atoms for the light to interact with, so it's got to kind of bounce off of all these different particles. For a less dense material, light can more or less go right through. It only has to interact with one or two particles. I don't know if that's fully right, but at least that picture makes sense in my head. It might be totally wrong, okay? So not super important to understand. What you need to know is that light has materials that it moves more slowly through than others. We can actually quantify this, how much a medium will slow down light, by calculating something known as the absolute index of refraction. We have a table right here, absolute indices, the plural of refraction, and that is in your reference tables. It is on page 2. Seems like we just looked at page 2 and now we're pretty much done with it. Absolute indices of refraction, right on page 2. This is the same thing that's right on here. What it tells you, a higher value means that the medium, that material, slows down light more. So we see the absolute indices of refraction. For air, it's 1. Air basically doesn't slow down light at all. Diamond is the highest at 2.42 on this table. Diamond really slows down light. And then there's all in between. Water, 1.33, doesn't slow down light quite as much. The calculation for the index of refraction, because there's an equation for it, is given in this table, right, or in this on page 5 right here. N, the index of refraction, absolute index of refraction, equals C, speed of light in a vacuum, divided by V, speed of light in a particular material. So I'm going to write that out. N equals C over V. Absolute index of refraction is N. C is the speed of light in a vacuum. V is the speed of light in some medium. Okay, in some medium. So N is a number that's assigned to that particular medium. V is the speed in that medium. This thing has no units. Okay, it is unitless. It is simply a constant that changes based on the medium. The way you can think of N, it is how many times greater C is than V. In other words, how many times greater the speed of light in a vacuum is than the speed of light in that particular material. If you had an index of refraction of 2, that would imply that the speed of light is twice as fast in a vacuum as it is in that particular material. It's a very simple equation. Let's do some math and see how it works. What is the index of refraction for a material in which light has a speed of 2.4 times 10 to the 8th meters per second? We write down N equals C over V. C is 3 times 10 to the 8th meters per second. If you ever forget that, it's right on the front of the reference tables. The speed in this material is 2.4 times 10 to the 8th meters per second. 3 times 10 to the 8th divided by 2.4 times 10 to the 8th is 1.25. N equals 1.25. So what that tells me is light is 1.25 times faster in a vacuum than it is in this particular material. And you'll notice there's tons of materials on here, but none of them is 1.25. That's fine. It's kind of like coefficient of friction. This isn't the exhaustive list of all the materials light can travel through, obviously. So we see that this is 1.25. That means light hasn't slowed down too much, okay, but it has slowed down some. Indices of refraction will always be greater than 1. Typically, you won't see anything too much above diamond, although it is possible to slow light down by a lot, and it's even possible in laboratories, scientists have actually stopped light. They've actually invented materials that light actually halts in. You'll never, ever see an index of refraction of less than 1, because that would imply that the speed of light is lower in a vacuum than in some material, in medium, and we know that light travels as fast as possible, as fast as it can in a vacuum. 3 times 10 to the 8th is the universal speed limit. One more example. What is the speed of light in sodium chloride? You go to this table, you look up sodium chloride, the index of refraction is 1.54. That tells me that light travels 1.54 times as fast in a vacuum as it does in sodium chloride. How fast is that? Set up the equation. 1.54 equals 3 times 10 to the 8th meters per second divided by V. Multiply both sides by V, then divide by 1.54. Do the math, actually write it out. If you are not sure of how to do that, if you get caught with stuff like this, please just write the math out. Don't try and do it in your head if you're a little nervous about it. 3 times 10 to the 8th divided by 1.54. Light travels at a rate of approximately 1.95 times 10 to the 8th meters per second in that sodium chloride. Now, the fact that this has been defined for us, this equation, this index of refraction equation, we can rearrange that equation and use it to get some interesting results, to see how the index of refraction affects not only the speed, but also the wavelength. I could rearrange this equation by multiplying both sides by v to get this. C equals n times v. Now, c is a constant. C is the speed of light in a vacuum. This suggests that n and v are inversely proportional to one another. If c is a constant, if n goes up, v goes down. And that makes sense because n is how many times faster the speed of light in a vacuum is than the speed of light in some material. If you have a high n, that means the speed must be very low compared to the speed of light. Since it's a constant, it's the speed of light in a vacuum, we could even write n1 v1 equals n2 v2. Since c is a constant and it never changes, this implies that the product of n1 and v1 is equal to the product of n2 and v2. That's the relationship for two different materials, two different media. I'm going to rearrange this though. I'm going to rearrange it to match something that's on the reference tables. I don't expect you to understand, wait, why are we rearranging this? I don't expect you to understand, oh yeah, that makes total sense. I'm going to write it like this. I'm going to divide both sides by n1. I'm going to divide both sides by v2. I end up with n2 over n1 equals v1 over v2. Okay, showing me that these are inversely related to each other. We're going to go one step further. We know that the velocity of a wave is equal to the frequency multiplied by the wavelength, and we know that the frequency of a wave as it transfers from one material to the next does not change. The wave has been created, the frequency is going to remain the same. That means I could even write this, n2 over n1 equals v1 over v2, meaning if n2 is greater than n1, then that also means that v1 is greater than v2. Higher n means a lower speed. Or excuse me, higher n means a lower speed. Yeah, that works. Okay. But I can take these and I can write it like this. F equals lambda 1 over F equals lambda 2. I cancel my F's out and I'm left with this. N2 over N1 equals V1 over V2 equals lambda 1 over lambda 2. The reason I show you this is because it's in the reference tables. It's right down here. Okay, exact same thing we did. This equation is just a time saver. If you're asked, let's say, okay, you have two indices of refraction. You have a light wave that starts in one material, it goes to another, and you know the indices of refraction of each, and then it says if the light wave had a wavelength of such and such in the first one, what is the wavelength in the second one? If you want to do it the long way, you would have to figure out the speed in that new material. Okay, you have to figure out the speed in the new material, then you'd have to figure out, based on the speed and the frequency, I mean, maybe you'd have to find the frequency yourself, then you could calculate the lambda. This uncomplicates that. This shows you the relationship between the index of refraction and the speed of the wave in the particular index of refraction and the wavelength of the wave as well. Ultimately, what it says is that n is inversely proportional to v, and since v is proportional to lambda, n is also inversely proportional to lambda, meaning if a wave goes from n1 to n2, and n2 is higher, okay, n2 is a bigger index of refraction, then that means that in order to make this equal, v1 must be higher than v2. In other words, it slowed down. In other words, if it slowed down, that means the wavelength decreased. So we're getting a full picture of the relationship between the index of refraction of the medium the speed of light in that medium and the wavelength of light in the medium. So all this has been talking about how the change in the speed of light when a light wave goes from one material to the next has affected things like, well, obviously the speed, but also the wavelength, and also what the index of refraction means. Let's go back to why we really cared about this. We know that the speed changes. The most visible proof of this is that the light bends. Remember, the light refracts. And what we have come up with to describe how much the light refracts, or to predict how much light refracts, how much the light wave bends when it goes into the new material, we've come up with a law that is known as Snell's law. This is the last equation that we will do in the waves section. Snell's law. Snell's law is given by this: n1 sine theta 1 equals n2 sine theta 2. Now, for Snell's law, I am not going to derive this. I'm not going to show you where it comes from. What we are going to do is experimentally verify it and practice with it, okay? We're going to do some demonstrations in class that show you how Snell's law works. We're going to do, well, there's going to be another video that shows you how Snell's law works. Basically, what we're doing here is we are verifying that this is a real thing. The left-hand side of Snell's law is typically used for the incident ray, the ray that is approaching the boundary. The right-hand side is used for the refracted ray, the ray that leaves the boundary in the new material. And since we are dealing with angles here, all of your calculations, this is a good time to remind you, need to be done in degrees. Okay? This equation does not work if you have your calculator set to radians. There's no reason for you to ever have your calculator in radians in this class. I know that's different from pre-calc, but you need to get used to flipping it back and forth. Sorry, nothing I can do about that. In our next class, we are going to practice with Snell's law, practice getting our answers with that, practice predicting how much or how the angle changes, what the angle of refraction or angle of incidence will be. Okay? One more waves video.